All right, hello everyone. This is Professor Brian Macon, and in today's video, we are going to talk about volume. So in the last video, we talked about volume, and we talked about the disc washer method. And in this section, we are going to talk about using cylindrical shells. This will be the method that we use. All right, so in the prior section, if I remember correctly, the example that we looked at was we looked at the region bounded by y equals x. Here was y equals x, and then y equals square root of x, which looks something like that. So we talked about taking the area bounded by those curves, and I think the first example we looked at was rotate around the x-axis. Let's consider, for the beginning conversation here, we're rotating around the y-axis. Right? So we're going to take that shaded region, we're going to rotate around the y-axis, and create a three-dimensional solid that which we're going to find the volume. Now in the prior video, when we talked about when creating disc or washers, what we would do is slice perpendicular to the axis of rotation. So for example, if we were using disc washer, we would slice perpendicular, let me pick a different color here, we would slice perpendicular to the axis of rotation. And when we rotated that, that would create a circular or disc, and then we would have this thickness would be delta y. We would have some delta y thickness here. Now, we are not doing that in this section, so let me erase this. Right, we're going to be looking at the shell method. So in this scenario, what we're going to do is slice parallel to the axis of rotation. So because we're rotating around the y-axis, we're going to slice parallel to the y-axis. And we're going to consider this region right here between the curves as generating the volume between the curves, right? No, excuse me, the volume of rotating those curves. So if we envision taking that particular piece of area and we rotate, what we're going to actually end up with is what we call a shell. Right? So we're going to have, that piece of area here rotating and creating a shell. Right? So for our shell, what we want to talk about is the surface area and how that creates a volume as well. Right? So we have two basic dimensions here, right? We have, in this case, the delta x, and the delta x gives us this thickness of the shell. Well, I'm not drawing the most pretty shells, so I'll come back and we'll try and look at a little better visualization of that in just a second. So what I'm looking at really is kind of like a cylinder here. Right? Now most textbooks call that a shell. Right? And that shell, in my opinion, is a cylinder. So we have the y-axis as the center of that cylinder. So it's kind of like having a ring, if you will. And if I have a ring that I wear on my finger, that's like a cylinder. So what I'm going to do is, let's say, take a pair of scissors, and I'm going to cut along the cylinder. And if I do that, that's going to give me a rectangle. I made that one a little too big, right? But if I fold that rectangle back together, it's going to create this cylindrical shell here. And so I grab this edge, let's say fold it back, tape it to this, it's going to create a ring or a shell, right? Or a cylinder. So first of all, we have a thickness to this cylinder. Right? I'll do my best to sketch that. Well, it's not too bad, right? So I have a thickness to that cylinder. The thickness to that cylinder is the delta x. So what we're going to do is we're going to take this area times the thickness, and that's going to create the volume. Right? So we talked about that in the last video. We're going to have the area of the shell, in this case, times the thickness. Right? So we just talked about, in this particular scenario, rotating around the y-axis, that thickness was a delta x. So in this case, what's the area of our shell? Well, it was pretty simple, right? We have let's call this the length of the shell. We have the width of the shell. Right? So for this shell, if we look at this dimension, the width, right, this dimension right here is the function height. So we're looking at the function height for this shell. Now, in particular, for this example, here's the height of my shell. It's the area between the curves. So in this case, the height of my shell is like the upper curve minus the lower curve, right? That's the thickness of my shell. Now, if we think about this for a second, let me try to draw here. Right? So the circumference of this cylinder or the shell is really my length. Right? So 2 pi r, if you will. Right? That's the length. Right? So this piece here, when I fold it back together, creates this here. Right? So that's my circumference, 2 pi r. Now my r is the distance from the line of rotation to here. That's going to be my radius. So the radius here is that distance. So that's just some arbitrary distance x, some horizontal distance. Now remember, technically what we're going to do, we're going to have, let's say, 10 of those rectangles, and then 20 of those rectangles, and then 50 of those rectangles. So the arbitrary rectangle is, let's say, at position x sub I. Right? We might have one at position 1, one at position 2, one at x equals 3, one at x equals 4, so on and so forth. We're going to let x sub I be the arbitrary representation. And then again, as we were talking about, what's the width of the rectangle? The width of the rectangle is this guy, right? This dimension here is this dimension here. We're only interested in the area between the curves. That is what's creating my entire shell. Right? So in this case, that is, upper minus lower, right? Let's call this, f of x. Let's call this g of x. So this is f of x minus g of x. Right? So there's my width. So there's the area of my shell, length times width. So let me scroll down here. And the volume of that shell is the area of the shell. So we have length times width. We have 2 pi x sub I. And then we have the function height at that particular x value. And then times the thickness. Now remember what we talked about in the last video was basically we have an area, so that's square units, times the thickness, and that's what gives us the cubic units. So we are creating a volume in that case. Again, remember we're doing, 10 rectangles, and we're doing 20 rectangles and 30 rectangles, and all of those rectangles rotate to create shells. So in this case, the volume of the region, right? Oops, I can't spell. Volume of the region is going to be the sum of those n rectangles. So here's the area of the ith rectangle times the width of that rectangle, giving me the volume, and I have, n of those. And then I'm going to take a limit as n goes to infinity. So, this is technically approximately, right? And then we're going to take a limit as n goes to infinity, and that's going to give me the exact volume of that region. I'm going to take the limit as n goes to infinity. I'm getting lazy, right? So I'm going to say, here's all of this stuff right here. Okay? And then that's going to give me, right? So remember what we talked about before. This is a Riemann sum. So that's going to give me the integral of 2 pi x. We have the area between the curves that rotates, and then the dx. And there's our integral, right? And then, we'd have some limits of integration there. So this is the quote-unquote formula for volume of rotation using the cylindrical shell method. Now we'll come back in a second and we'll take a look at a specific example like the one that we originally wrote. So we had used this simulation yesterday, and we used the disk method, right? So here's an example of rotating around the y-axis, and if we did a disk, we slice perpendicular to our axis of rotation, right? And when we rotate that, we create the disk or the washer. And again, the area of the surface, or should say the face, is pi r squared, and the thickness in this case was a delta y. So we talked about that in the last video. This scenario, we're doing a shell, right? So again, here's our axis of rotation. We're going to slice parallel to that axis. And notice we're going to have a little gap here, right, like we did in our scenario. So when I rotate this gap doesn't create any volume, only this region here. So as I rotate, we can see our shell, right? And then there's, what I call the cylinder, right? So if we take this cylinder and we cut it and open it up, that's our rectangle, kind of like that. All right, there's my rectangle, if you will. Visually, it's not really accurate, right? But if we look at this guy, right, when I cut open that cylinder, there's my rectangle, right? So visually, that is how we generate the shell. We slice our area, our piece of area, parallel to the axis of rotation, and then as we rotate, that generates a cylinder or a shell. Right? Now, let me come back to our notes. Right? Remember, we talked about the what do I want to say? The length of the rectangle was the circumference of this circle. Right? So the circumference of this circle was the length of that rectangle, and that was our 2 pi r. That's the circumference of the circle. Right? Now again, the radius of this circle, right? The radius of this circle right here comes from this distance to that rectangle, the x sub I. Right? That's my radius. So there's my 2 pi x, and then the height of this shell is the area between the curves, and that's our f minus g. Right? So here's my length times width, and then the thickness that gives us the volume. So there's a better visualization than I can sketch for you, right? Again, we have some x value where each of the rectangles are going to exist, and that's our radius of our shell. Again, we can see the radius of our shell is the distance to that vertical rectangle we drew. And then when we rotate that, right, that radius really gives us a rectangle when we slice it open. All right, so again, technically, we're going to do this for, let's say, 10 rectangles, right? So here's another rectangle. Here's another rectangle. Those are coming out really sloppy. Right? Here's another rectangle here. Right? So we're looking at the areas between the curves on those rectangles. And each of those rotate and give me a particular shell. Right? Again, the beauty of the limit process is I might start with 5 shells. I might then move to 10 shells, and then to 20, and then to 30. And in general, we have n of those shells. That's an approximation that we have right here. And then when we take a limit, as n goes to infinity, that's a Riemann sum. And that gives us the integral. Right? All right, now let's come back to that prior example. I got a little sidetracked doing this in an arbitrary fashion. So let's come back to that original example. That original example looks something like this. So we had the curve y equals root x, and then we had y equals x. Right? So again, since I'm using cylindrical shells, I'm going to slice parallel to my axis of rotation. So if this is my axis of rotation, I'm going to slice parallel to that. And then when I rotate that, it's going to give me a particular shell. And the volume of that shell is going to be 2 pi x. And then I'm going to have the upper curve minus the lower curve. And dx. So the way that I like to think of this here, right, this is like the area between the curves. When I look at this rectangle here in particular, it's the area between the curves that rotates and creates that shell. Right? So I like to think of it in that manner. Right? And then technically, we have A to B as our limits of integration. And if you think about this, what we did when we did areas of curves, we found these points of intersection. So I need to find those points of intersection, and that's going to give me those limits of integration there. All right, so let's plug in everything we know first. So the first thing I'm going to plug in here is I got the 2 pi x, and then my top curve is the root function that we have here. So that's going to be root x. And then my lower curve is the linear function. So there's everything plugged into the integral, and then I need my limits of integration. So to find those limits of integration, like we talked about in our last video, we're going to set the two equations equal to each other. And, in this case, I'm going to go ahead and square both sides. So if I square both sides, I get that guy. And then let's say I subtract the x over, and I get that. And then I'll factor out a common x we have there. And I'll have x minus 1 equal to 0. So I set this factor equal to 0. I set this factor equal to 0, and I get those 2 points of intersection, and those are my limits of integration. Okay, so back up here in my graph on the top of my screen, I have 0 and 1 as those x limits of integration, and there's the setup of my integral. Right? Oops. There we go. Right? There's the setup of my integral. Now, if I'm going to evaluate this integral, right, I need to go ahead and move through the process here. Technically, what we're about to do is not new, right? This would be a Calc 1 integral, right? So what's new is this setup that we just wrote. So if we're going to evaluate the integral, right, we're going to take the 2 pi out. This is x to the 1/2 times x to the first. I add the exponents. And then x times x is negative x squared. And I'm evaluating from 0 to 1. Right, so I'm going to find the antiderivative. So I'm going to add 1 to the exponent. That's going to give me 5/2, and I multiply by the reciprocal. And then add 1 to the exponent and multiply by the reciprocal. I'm going to evaluate 0 to 1, and whatever numerical we get out of there is our volume. So let's see, this works out nice, because when I plug 1 in, 1 to any power is just 1. So I'm going to get 2/5 minus 1/3. And then when I plug the 0 in, that gives me a big old 0. So I'm going to end up with 2/5 minus 1/3, and then minus 2 pi, and then, 0 minus 0. So that works out kind of nice and pretty. And then I just need to get a common denominator here. So let's see, 15's the common denominator. I would have to multiply this by 3. And this by 3, so that gives me 6. I have to multiply this by 5 and this by 5. So I'm going to end up with 1/15 times 2 pi. And there's my volume. Also, keep in mind, this is a volume measurement. So whatever my units were, those are going to be cubic units. And there's the volume for that particular example. Okay, so that is a cylindrical shell. Cylindrical shell is what I create by rotating around the y-axis in this case. I'm going to slice parallel to my axis of rotation. So I want to take a look at a couple other examples, and that'll really close up this conversation of cylindrical shells. So let's suppose that, let's take that same example, and let's suppose we rotate it around the x-axis. Right? So let's take that same example, and let's rotate around the x-axis. So let me just redraw that picture. Here's that picture. We had the curve y equals x, and we had the curve y equals root x. Now remember, we already did the work of finding the points of intersection. So this was x equals 0 and x equals 1. And y and x are the same. So if x is 1, y is 1. So this is the y limit of integration. And then the x limit of integration, again, is 0. So here's my region. And let's suppose that we're rotating about the x-axis. Remember, what we just talked about was that if I'm rotating around the x-axis for a shell, I need to slice parallel to that axis of rotation. And therefore, I'm looking at that particular shell that's going to rotate. Right? Now again, I'm going to do my best. Right? I'm going to rotate, and that's going to create a shell for me. Say something like that. There's my shell. Right? All right, now for that shell, keep in mind there's a radius. So this radius is a y distance. Right? I'm looking at a y distance here, vertical y distance. So my circumference of that circle is 2 pi y, right? 2 pi r, and my circumference is y. Right? Excuse me, my radius is y, so my circumference, 2 pi r, is 2 pi y. So instead of the 2 pi x that we had, we now have 2 pi y. And then the thickness, right, the thickness of the shell right here is a delta y. This is a delta y. So the thickness of that shell, right, is going to be, what creates the volume here of my my shell, my cylinder. That's how I like to think of that, right? So there's my delta y here. So I'm going to have the delta y. Oops, I'm writing my integral. 2 pi y. I have my dy, and then I need the area between the curves. Right, so the height of this shell is the area between the curves. So I have the upper curve and the lower curve in relation to the y-axis. Now, I want to point out to you, keep in mind that when I have a dy, everything needs to be in terms of y. So when I look at this as being my upper curve here, what I'm going to think of is it's x equals y. X equals y is the equation of that curve. And then my lower curve here is the root function. But what I need is this in terms of y. So y squared equals x for that curve. So I have y squared equals x for that curve. Right, again, let me point this out to you. This may or may not be obvious. So when I'm finding the distance to the upper curve, remember this is a horizontal x distance. So that's why we're writing that as x equals y. Right? And then the distance to this lower curve here, right, is from the line of rotation. So that is a horizontal x distance as well. So that's why we have to solve that equation for x to get y squared. And again, the reminder is that I have dy as my integral. That's the reminder. Okay. All right, and then the only thing left over is we need to look at y limits of integration. So this area bounded by these two curves lives between 0 and 1 on the y-axis. So I'm going to have 0 to 1 on the y-axis. Now we just completed this problem where we rotated around the y-axis and we had limits of integration of 0 to 1. Right? We were using these limits on the prior problem. It's just coincidence that these are equivalent, 0 to 1. So please keep that in mind. I'm using y limits of integration for my y variable. Right, and then I'm not going to go ahead and evaluate that integral. I'll leave that for you to do. But here would be the setup. If I was setting up this integral, right, here's the setup of that integral, and then I would evaluate that integral to find the volume using the shell method. So here's what I want to do. I want to find the volume of the same region two different ways. So for example, I want to look at a problem where we're going to rotate around, let's say, the particular axis, and we're going to use the shell method first, and then we're going to use the disc washer method next. And let's compare what those results would be in that scenario. All right, so listen, I think actually to save a little bit of time, let's compare two regions that we've already done. So I'll remind you, in the last video that we did, we looked at the same region. We looked at y equals x, and we looked at y equals root x. And we used the disc washer method to create the volume of rotating around the x-axis. So for disc washer, again, I want to remind you, when the x-axis was the line of rotation, we sliced perpendicular to that line of rotation, and that's what created our, our disc or our donut or a washer. So we had to find the area and the thickness of the washer. So the area was a pi r squared. So here was our pi r squared. And then our thickness of our disk here was a difference of x values. Our delta x was our thickness. Right? So we ended up writing our formula of pi r squared minus pi r squared. Right? That would be the difference of the two circles times the dx. Now for this particular example, here was the setup. We had, for the rectangle drawn perpendicular to the axis of rotation, right, that creates our donut, our upper curve, our outer radius, was the root function, so there was that guy, and then our inner radius was to the line y equals x, so there was that guy, and then we had our dx. Again, I just want to point this out to you. Here's one of the things that I think of when I draw these. Right? When I drew this rectangle, the thickness of this rectangle was a delta x. So that tells me that my entire integral, right, my delta x, my entire integral needs to be in terms of x's. So there was our setup. And then we came down here and we evaluated that integral. We went ahead and did the antiderivative, and we got pi over 6 units. So the notes that we were just writing was the same scenario. We took that same region and we rotated around the x-axis, and this time we did the shell method. So since our line of rotation was the x-axis, we drew this shell parallel. So that would be horizontal. And when we rotate that rectangle, we rotate around the x-axis, we created the rectangle of area, horizontal, right, parallel to the line of rotation. When we rotate that, that creates the shell. Again, in this case, the thickness of that rectangle is a delta y, so there's our dy. And then we have to do, basically upper minus lower from the line of rotation. So our further curve was x equals y, so there was that guy. And then the inner curve was the root function. So there's that guy. Now remember, the root function in this case was x equals y squared. Right? So there was that guy. Now, so in order to compare, we need to evaluate this integral. So let's go ahead and evaluate this integral. And this will save us a little bit of time in terms of comparing the two methods. Now obviously we should get the exact same volume. Right? We're taking the same region between root x and x, and we're rotating around the x-axis. So when we did the disc washer method, we got, I think that was pi over 6. Now we're using the shell method. Still the same volume, just a different method. So then let's go ahead and evaluate this integral. Right? So I'm going to pull the 2 pi out. Whoa, what's going on? This thing has a mind of its own, and it hates me. I think you guys have heard me say that before. So I'm going to pull that 2 pi out, and it jumped down. So let's try that again. I'm going to pull the 2 pi out, and then I'm going to go ahead and distribute. Y times y is y squared. Y times y squared is y cubed, and then dy. Right? And we have our limits of integration, 0 to 1. I'm going to have 2 pi, and let's see, antiderivative of y squared is 1/3 y cubed. Antiderivative of y cubed is 1/4 y to the 4th, and I'm going to evaluate 0 to 1. So again, I'm going to plug the 1 in, and when I plug the 1 in, 1 cubed, 1 to the 4th, that's 1. I'm going to get 1/3 minus 1/4 when I do that. And then when I plug in the bottom limit of 0, that's going to give me 0 minus 0, which is all 0, right? So then I'm just going to common denominator here, common denominator, so common denominator would be 12. So I got to multiply this by 4. I'm going to multiply this by 4. And then I got to multiply this by 3. So I'm going to multiply this by 3. And then I get, what is that, 2 pi times 1/12, and then we can see the 2 and the 12 reduce. 2 pi times 1/6, and that was what we had from the disc washer method. All right. So again, same volume, slightly different technique. One disc washer, one shell. Right. So here was our shell method approach, and again I forget. All right. So there's our pi over 6 cubic units from the disc washer method.